Welcome to all of you for this Cree talk number 58. Today we have the second talk by Shri Jattana, who gave an earlier talk 1 month ago on the semiconductor manufacturing thing. And based on the request from some of the participants and others, we had requested him to give a follow-up talk. So thank you, sir, for agreeing to give this follow-up talk. For those who are not aware of Shri Jattana, he was the former group head at SCL Chandigarh and has been in the semiconductor manufacturing for more than 3 decades. And he's also an adjunct faculty with some institutions currently. And he has also done, while in SCL, he has done a lot of work for ISRO and was also given an award for the services offered to ISRO. So with this short background, let me invite Sri Jattana to share his second talk on semiconductor manufacturing. Over to you, sir.
So, thank you, sir. So I will share the screen and then. So this is the complete flow of any VLSI circuit silicon chip, starting from the specification to final qualified product, and it starts with the definition of the product, freezing the technical specifications, and then design. Design is done in various stages, various steps, and it takes more time. And after the design, the designer, they will give some information in a particular format, which we call it a GDS. So that is a tape out. And the format GDS will contain certain information. Based on that information, the mask fab will prepare masks, and those masks are used in the fabrication of the device. So depending on the technology, there can be 21, 22 masks, or it can be around 50, 54 or 55. One mask normally takes 1.5 day. And so if there is a product which has 30 masks, so 30 mask sets, so it will take 45 or 50 days for the complete fabrication. And then the wafer will come out, and the wafer will be tested. On that wafer, there will be a number of dies. Each die will be tested, it will be packaged. After packaging, it will be tested. Then there are certain environmental tests, testing at high temperature, low temperature, subjecting the devices to various other environmental changes and giving the shock to the devices, and centrifuge test, giving certain vibrations to the device, and all those things are done. And then finally the device is ready, the product is ready to be given to the market. So this particular, I will focus only on the fabrication, some key points in the fabrication. So the fabrication part is also known as a process. So we call it a process technology. In brief, like if I draw the sketch of a MOS device, which is a metal oxide semiconductor, and this is a cross section, and we will start with P substrate wafers. So we will start with these wafers, and normally these are 12-inch wafers and around 825 micron thick. And on these, various layers are deposited on top of it. And the basic topology of a MOSFET, if we see, it's basically, it has a gate, it has a source, it has a drain, and there is a well under which these devices are made. So, and then the next device will be on the side of this. So we will have the various modules, like this is a well, so we will call it a well engineering. There are issues how to make these wells. Two wells, there will be another well here, and two wells will be separated. So that is known as isolation. Like in a two houses, there is a boundary wall. The same concept, two devices have to be separated. There should not be any crosstalk between them, leakages between them. And then there is a gate. Gate is a very sensitive. It's gate terminal is the terminal which controls the flow of current from source to the drain. Then how to make these gates? There are various layers used in these gates. Various chemicals, various processes happen. And then there is a source and drain. They are also made. And after that, we have to make contacts on this, and we have to put some metal to make contact. And there can be numerous number of metal lines, like in a PCB. There can be around 8 to 12 different metal lines. And the reason is we want to have more and more component density. And if, for example, if there are 4 devices and each device has 4 connections, each device has 4 connections. So there will be an interconnection between these devices. Like this may go here, this may go here, this may go here also, and may go here also. And so these connections cannot be done like I have sketched here. There is a way of doing it. And moreover, these connections also take space. They also take silicon. So if I want to make a very compact, if I want to make a very high component density, I want to make it very close to each other, then I won't get the enough space for making these contacts. So what I can do is I can go for more metal layers. I can go for more layers on top of it. Like we have multi-storied flats. The concept is the same. Area is limited, so you build high-rise buildings. The same way here, because our interest is to have more components. So in a process, technology, there are various types of technology. Let's not go into that. Presently, 5 nanometer is the latest one, and then there is a 7 nanometer also, and 3 nanometer. TSMC is saying targeting 3 nanometer will be in operation maybe by the end of the next year. And 5 nanometer, there's very interesting news. I think around 10 days back, and around 40% of 5 nanometer capacity has been booked by one company who is making GPUs for AI ML. And Apple also has around 25-30% of that capacity of TSMC is utilizing for making processor for their iPhones and other iPads, laptops, and some other devices. So all these lower, you can say nanometer, sub-nanometer technologies, they are basically used for processors and memories. So the nanometer, what this 573 nanometer means? Actually, though it's not a correct, but for simplicity, I can tell that it means the channel, this particularly channel, how the distance between source and drain, and till 45 nanometer. So that was the minimum dimension, the channel length, what we call it technically. But lower than 20 nanometer, it's not the channel length. Channel lengths are more. There may be around 14, 15 nanometer. So there is no dimension which is of 5 nanometer actually size. All the dimensions are of more than 13, 14 nanometer. They are between 14 nanometer and 20 nanometer. It's just a name which is given. So then you will ask, then what is the difference between 7 and 5? The difference is in the architecture, in the topology of the device, the dimensions may be same, but when you go from 7 nanometer to 5 nanometer, the designer gets some advantage, and that advantage is in terms of speed. He gets 10% or 15% more speed. Or if he is not getting the speed, he gets less power, the same functionality at less power. So that's how they have given this name of this technology node to 7, 3, and 2 or 1, and where it will stop, I think maybe 2 and 1, it will stop. And these kind of devices, and this device which I have drawn is basically a planar, and that also is valid till 20 nanometer. Below 20 nanometer, there are FinFETs and 3 nodes and 3 generations. Below 7 nanometer, there is a gate all around, and that's a different direction. But there is a huge variety of different technology, which I mean process flavors, process nodes, and all those things are there. So we will not go elaborately into all these things. And the purpose of showing all these slides is like it's a very complicated, you can say, operations which are being done. And at 90 nanometer, there are close to 850 steps, process steps. And those steps, as I told you, they are basically for that. For isolation, for well formation, for isolation, there may be around close to 30 to 40 steps. For well, there may be many steps for making the well, which is called it a well engineering. For a gate stack, there will be many steps. And once you do each, like after each operation, the wafers are cleaned. And cleaning also, it's not that simple. It's a they are cleaned by acid, they are cleaned by bases, then they are cleaned by pure water, ultra pure water. So there are a number of steps in the cleaning, and there are recipes for that. And the reason is because it's a chemical reaction. Something, some particle may be sticking, which may not go with water, which may not go with base. It will only go with some acid. And those are all standard things, how to clean, and enough experiences for the past 30, 40 years in this industry. So all these things have been standardized. So a lot of standardization is there. So this 3 nanometer, 4 nanometer, which I was saying, is the latest, and only TSMC is doing. And recent, there was a news which were saying NVIDIA, which is a company which is making GPUs for AI/ML. So their valuation is close to 5 trillion US dollar. So you 5 trillion US dollar, the valuation of one company who is making processors or GPUs, which are widely used nowadays for AI/ML. And our Indian economy is 4.2 billion, 4.2 trillion dollars. And some economists say that it's not 4.2, it's less, it's close to 3.6 or 3.6 or 3.75. Even if it is 4.2 trillion, NVIDIA is 5 trillion valuation. So you can compare one company, and they are only making processors, GPUs. And nowadays, AI/ML is driving this particular industry, because you want AI/ML will have huge applications in everywhere. It will have in a washing machine, your phone, and your telephone, and everywhere there will be AI/ML running. And you need very, very fast processors. And very fast processor means you need lot of you can say computing power. Either there has to be a changes in the processor architecture, or you can have more cores. That way also parallel processing, you can increase the computing power of a processor. As in our laptops, the chips which are used, they have 4 cores or 8 cores. So it increases the computing power. If we have 8 core, it increases the computing power by a factor of 5 or 6. So all those things are happening, and so that's why this particular thing has become very, very interesting. So the silicon wafers, bare wafer, then there are people who make only wafers. That also is a long process, but they will make wafers only, and the wafer will look like this. And I can show you last time, this also I showed. If you are able to see, this is a plain wafer. This surface is just like a mirror finish. And these are standard, diameter, thickness, everything is standard. And these wafers are shipped by the company in a boxes. If you see like this, this is a standard sizes. All this is standardized, and each box contains 25 of these wafers. And let me open this. You can, if you are able to see, this is how these wafers are kept. If you are able to see, this all these, there are 25 slots. Slot 1, 2, 3, like this. This is one wafer here, and it goes like this. And this is how they are done. So they are shipped by the people who make these wafers. by the company. They are shipped to the fab, to the foundry. Within the foundry, the boxes which are used, they are similar, but they are more, you can say, better quality than this. And there is a ESD protection and a lot of other things in this. And these are the standard things. So 300 wafer is the standard, and when we get the wafer after fabrication, it will look like this. There, as shown here, there will be a lot of polygons, rectangles, which are each die. I don't know how much it's clear. So it will look like this. And so I will skip this. So let's see what are the major bottlenecks. Why in India we didn't have any commercial fab for the last 15-20 years. So there I have listed 5. It's a very capital intensive. Making a fab is basically you require a lot of funds. If you have to make a fab of below 20 nanometer distal fab, you will need at least $20 billion is the budget. And for analog fab, $5 to $10 billion are needed. And litho is a machine which there is only one company which makes that, ASML. It's a Netherlands company in based in Netherlands, but the technology was developed in collaboration with the US government and IBM and Intel. TSMC also invested huge in these. So this litho tools are very, very expensive, and each process they has to number of steps in the litho or more. So you should have one should have in a fab many litho machines are required depending on the production level, and there is only one supplier. And for if you have to do fabrication of below 10 nanometer, you need those kind of extreme ultraviolet machines which are close to 400 to 500 million dollars. And not only that, the delivery period, the delivery time is nowadays is 1 year, more than 1 year even, because that ASML can produce limited equipment, such sophisticated equipment in a year. So delivery time are also huge, and they only make 50 to 60 units. So TSMC has taken bulk of these machines, and Intel is facing delays due to limited adoption, affecting their 7 nanometer roadmap. And another is the depot, the tools on which we deposit, which are used in depositing certain layers, certain chemicals, and the tools which are used to do to etch certain areas. So they are atomic layer deposition. We can deposit atom by atom, and then chemical vapor deposition. So these tools are there, which are from applied materials. They are also expensive, and special lot of tools are required when you have to create a high aspect ratio structure like this. High aspect ratio, if I have to make a cavity like this, so then this etching, if I have to do at 90-degree, or if I have to do at a certain angle like this, and which is required in case of isolation. So these required certain sophisticated etching tools. Etching and depot both go simultaneously. So these kind of tools are also expensive, and this is also one of the bottleneck. And the companies strategize by multi-vendor sourcing, and there also the companies are few only: Applied Materials, Lam, and Tel, Tokyo Electron Limited. So these are the two. In each particular process, the tool which is used is made by only one or two, or at the most 3 companies only. So they have the monopoly in this. Then a lot of metrology and inspection equipments are needed. And because whatever steps, whatever layer, whatever pattern you have made, so whether the geometry is exact or not, you have to verify that. And not only you have to see that there is no dust particle setting, there is no any extra particle setting. It's a chemical reaction. There the byproduct has to be eliminated. So there is no particle of the byproduct which is sitting on the chip. So these inspection, because it will affect your yield, and if your yield is bad, it will directly, like, you are losing money in that. So KLA is a company which makes these inspection tools, and these tools are also very expensive. 15 million, they are required in large number, because we are doing these companies are doing 50,000 wafers per month. 50,000 wafer starts per month, and 12-inch size wafer. So these tools are required in hundreds, and so that is the reason the cost of putting one fab is in billions kind of thing. And nowadays AI also is used to a lot of extent by seeing whether the structure which we have printed is correct or not, whether there is any particle which is sitting, if the size of the particle is more, whether it will affect the yield or not. So that information can be tackled by AI driven softwares. And many companies have made these things, and they have cut down on the metrology cost and using AI software and saving millions per fab and things like that. So a lot of application of AI in each particular area, in each particular, even in the manufacturing of these equipment also. Then the entire fab area has to be a clean room. One has to maintain a particular temperature, humidity, pressure, and things like that. So we need very ultra clean air. So from the atmosphere, air is taken, air is then purified, temperature, humidities are maintained, pressure is maintained. So a lot of filters, HEPA filter, they are very expensive. They have to be replaced every 6 months. So all those things are done. So that is the reason maintaining all these things also costs, and the capital cost is also high. Then there are a lot of equipments, a lot of gases and chemicals which are required, which we call it as specialty gases are there, precursors are there. Silicon wafers, as I told, there are companies who will make only the wafers, and fab will take those wafers and do the processing on those. So now there is no single country, there is nothing like Atmanirbhar in this area. There is no single country which is doing everything. Like TSMC is a fab. It's in Taiwan. It's they manufacture around 63-64% of the total world's production of chips. But they are not manufacturing silicon wafers. They are taking wafers from other places. They are not manufacturing equipment. There are companies which are based in Japan, America, Germany, Netherlands, like that. And then they are not testing the wafers. They are doing only wafers. Testing is being done in Malaysia and other things, at Philippines, a lot of Singapore, Hong Kong, Malaysia, and some other countries. China also is coming in a big way. So you have to make collaboration in this. Even in US also, a lot of these technologies were developed in America only. And but mass manufacturing is not done there. But now they are focusing. They are putting 2-3 fabs to do mass produce these chips. So these are few of the bottleneck why in India we didn't have a commercial fab, though there is one fab which is an SCL fab, and it's a 180 node. 180 node is good enough to make devices for military space, railways, and things like that. But we cannot make devices, processor which can be used in laptops or iPhones and things like that. And that is the view of the. This is a view of a machine. It's a one part of extreme ultraviolet, which is being made by ASML, and billions of dollars were spent for 20 years of research in making these equipment. To ship this equipment, it takes 5 aircrafts load. So, and this is one part of that machine. So, think these things are quite complicated. And as you can see, these are some of the mirrors which are being used in that machine. And so now it's a very, you can say, crude analogy, but like we can say we have seen multi-storied buildings. So you can we can compare the fabrication of a chip as analogous to a multi-storied building. We have a base material, we have a foundation. Here we have a silicon wafer. As I told, we are starting with a wafer. and which may be P type or N type. It's never a pure silicon. It has to be a doped silicon. It it should have some resistivity depending on the technology, and either P or N type, and the thickness of the wafer, the diameter, and it has to be 100 orientation for CMOS, and those things are clear. So it's just like foundation, and on top of this, we will make the device. Like in a building, there may be many floors, there may be many different materials, many layers, many different processes. Like RCC, there may be 3-4 different materials for making RCC, then thickness of RCC, the composition of those materials, how it is made. There also is some rough chemical reaction is there between 3-4 materials, and how those particles stick to the steel rods. And then flooring is different, then walls are different. And then we have seen a lot of pipes going from one floor to another floor, which will be carrying water, electricity, and sewer and things like that. So in the same way here, we will have a lot of pipes moving, a lot of metal moving, and there can be around 6 to 12 or 13 different metal lines. And here, between two metal lines, there has to be a insulating material. So it's like, and like in a house, the process is different. Like for an RCC, making an RCC, and for making a floor tiles, the materials are different, the process are different. In the same way, so many layers are being deposited, and the processes are different, the chemicals are different, they are being done at different temperatures. So it's a very crude analogy, but it's just like that. And in building also, the architect will make a complete plan, about how the drawing, and based on that drawing, he will construct that building, where that pipe is, where that sewer pipe, where the water pipe, and all that. In the same way, this also, the designer has made the design, and the designer information is given in terms of GDS file. GDS, there GDS contains all that. It will contain the information of each layer. Within that layer, how many layers to be used, and that information is there in the GDS. And then there is a technology file, the process. The each step has to be done. That is a recipe. So these two things combined, it will go in a fab to manufacture that particular part. So this is how it goes like. So I will explain one step in quite detail, the one step, and from that one can get an idea that how the further steps will be. And so there are 5 basic actions in this. Like we will be adding materials, and adding materials or adding films, what we call it a thin film, because all these dimensions, they are in micron, they are less than 1 micron, they are in nanometers or angstroms, 400 angstroms, 5000 angstroms, 5 nanometer, 500 nanometer, like that. So we are depositing a certain material or adding a material. Another is we are removing the material also, because we want to make a pattern. And I have a 8-inch wafer. So what I will do is I will like deposit aluminium on the entire wafer. But I don't want on the entire wafer. I want these 2 lines of aluminium only. So this means I have to see the other areas. I have to remove the aluminium from other areas, so that only these 2 lines are there. So that is the etching, and there are various processes for etching: dry etching, wet etching, and like that. Photolithography tells that in this area I have to protect these lines only, so that mask will tell. So that mask and mask information will be there in photolithography as shown here. So this yellow thing was there on the entire thing. Now here it has been removed. So that information is there in the mask, like here is it shown. And I have a mask here which will not be able to see much. So this is one reticle, and this is the size of the reticle is 26 mm by 26 mm. Structure is repeated, and this is one mask. It's in a box. I cannot open this box, and This is basically of a quartz, and one mask cost around 500 five $7,500 to maybe around 15K or 20K dollars, US dollars. So the mask sets are expensive, and they contain this information. And masks are made from the GDS, which is submitted by the designer, depending on the design of the circuit. Another thing, the process is implants. Silicon, pure silicon, which we call it intrinsic silicon. It's basically an insulator, and in pure silicon is basically insulator at room temperature. It has 10 raised to the power 10 electrons and 10 raised to the power 10 holes at room temperature, which is known as in physics intrinsic carrier concentration, Ni. But still it is an insulator, and the reason is because silicon atoms are 10 raised to the power 22 per centimeter cube. So in 10 raised to the power 22 centimeter cube, we have only 10 raised to the power 10 electrons. So for 10 raised to the power 12 silicon atom, we have one electron. It cannot constitute a current. So the way metals and insulators are described in electrical engineering is in terms of resistivity. So metals, they have resistance. Resistivity is very in milliohms. Insulators are more than megaohms. Another way is to describe the difference between these two is in terms of charge carriers. So the charge carriers, if they are more than 10 raised to the power 10, and then it comes under metals. And the charge carriers are less than 10 raised to the power 10, then it comes under insulators. And in between, there are material which we call it a semiconductor, like silicon or a germanium. The reason is this 10 raised to the power 10, which are mobile carriers, charge carriers, in terms electrons and holes, these can be increased, and we can increase these to 10 raised to the power 15, 10 raised to the power 16 by four different methods: by shining light, by subjecting this to electric field, or by implanting some boron by some dopant elements, which is a column 3 and column 5, boron or phosphorus and things like that. So that is known as implantation. So implantation is also used a lot, like we have to make a well. There will be many implants in that. For making a source and drain, there will be many implants in that. So this is one process. And then metrology, of course, whatever we are doing, you have to test, like you have made this structure, you have to see whether this geometry is basically as per you, as per our requirement or not. So this picture gives like how much time in the manufacturing area. Wet processes will take 24%, and metrology will take 10%, and dry etching will take 13%. Implant will take 8%. It's like that to get you an idea of these different processes. So as I told, there will be different masks. So each masks are named. Like for example, N-well means for making N-well, there is a mask. For making P-well, there is another mask. For making active area, there is a mask. For making gates, there is a mask, like this. And each, there is a code, and so these masks will have that information. Like this particular mask, which I am showing, this is for a contact mask. This particular mask has information of the contact only. And so each particular layer will have a different masks. So in a traveler, then like in a process, there will be different, you see, there will be different features, there will be different flavors depending on the designer, which flavor he has used. So the batch card is made. The batch card will give the entire information. All these 700 steps will be there, starting from the step 1 to wafer start. Then what is the next step? What is the third? Like this. So that in a traveler or a batch card, that information will be there. And like here, it's written pad oxide growth. You have to grow an oxide, and it will be, that information will be there. It's a step under diffusion. It will go to the diffusion area, and then there will be recipe, and how, whether it's a wet oxidation, dry oxidation, whether it's oxygen only or it's oxygen plus water, what temperature, what pressure, how much time, how to do that. So all information will be there in a recipe, in a process recipe, which is there in the stored in the machine, and the recipe has a number. So that information will be there in the traveler, and the technician there, once he gets this a set of 25 wafers, he will take that, he will program that particular, because he will have this information, the traveler also, and that the recipe number will be there. So he will fix that recipe, and then this box, the robotic arm will take that box inside that, and will open it and take one wafer, put it at the furnace in a boat, in a furnace where these wafers are put, that is called a boat. And the furnace capacity is more. One furnace can have 200 or 300 wafers at a time, it can handle. And so the slots where these wafers are put, so that are fixed, and that numbers are fixed. And after any process, they are kept back in that box in the same slot. Like if a wafer is taken from slot number 3, it goes to the boat, and from the boat, when the process is over, it will go back to the same slot. So all this information is being done by robotic arms and things like that. Lot of software is there, and it's a very well managed system. So the first step is, we are starting the wafer. We have to make whatever the node, whether it's a 40 nanometer, 20 nanometer, or 30 nanometer. Normally, the first step will be to grow an oxide, and to grow a base oxide. That is the first step. And there, after this, like this is a silicon substrate, and we will grow an oxide. The reason is, we have to earmark the areas where components will be made, where components will not be made. So in this, for example, it's a 4.5 micron area is shown. The wafers will be 12 inch. So this picture is only shown for 4.5 micron. So in this area, what I have to do is, I have to keep this area, like I will say this is my active area. Active area means here components will be there. Then this much area is field area, and this much area is field area. Field area means this is isolation. This has to, and then another active area. Then again isolation, like this. So it's just like in a demarcation in a house. So if you have a plot, we go there and they will demarcate that, and then we will construct a boundary wall. So that is the reason. So these areas are decided first, and where the boundary walls are the isolation areas, and how to make this isolation area we will see, and what are the issues in this, then we will see. And once we get this active area, there the transistors are made, and the first well will be made, then gate will be made, gate stack, then source drain will be made, then contact will be made, then metal 1 will come, then again, if there is a metal 2, then metal 2 will come, then metal 2 to metal 1, there is a connection which we call it a via, and things like that, it is there. It's like this, it goes on. So here in this figure, we have started with the P substrate, with the P-type wafer we have started. It's a lightly doped. The wafers which are used, we call it a substrate. It's not a intrinsic silicon, it's basically a doped silicon, and the resistivity can be from 1 ohm centimeter, it can vary to some 100 ohms per centimeter. And if it is for more than, and for some like power devices which which handle power close to 1 kilowatt kind of thing, the resistivity is quite high, 1 kilo ohm centimeter also. So normally, and for CMOS, like processor and memories, they will have 1 ohm to some 100 ohm centimeter, and the process engineer, they will decide what these specifications are. So this is the wafer 300 size, and we used to play these in our school days, LP records, which we call it a long play. So it is also of almost of the same size. That is why I have put it here. So this is the picture of a Micron. Micron is a leading company which is making memory. It has around 35% share in it's American company, 35% memory business. Pen drives. The memory which is used in the pen drive, basically it's a NAND flash. So it's made by this company. So just to give you an idea of the dimension, this human hair, this is the human hair. These are the real pictures taken. And this is the memory array. This is the human hair. Let's see the next. So this is the human hair, and this is the some memory arrays, and this scale is 100 micron from here to here. So you can say human hair can vary, I think from 30 micro to 100 micro. A very thick hair can be 100 micro. So this is one human hair. So you have so much of circuitry in one human hair. And what is that? And if you see that, so there are 2, 3 more slides which are not coming. But if you, I have few slides where this particular area is also blown up. So this much area, it is storing close to 1 kilobits of memory. So 1 kilobit of memory, it is storing this much line, a line which is equivalent to 60 micron of the area which is close to our human hair. So this is the comparison. Our blood cells, if they are of this size, then 1 bit circuit which store 1 bit is of this size. This is the comparison. There is some picture in the, I don't have now, there is some picture in the Google which is saying, and it's actual picture they have taken. If the red blood RBC cell is this much, 1 bit circuit, it has around 6 transistors. It will look like this. So the overall size of one transistor will be in nanometers, maybe 100 to 150 nanometer area it will be occupying. But the viruses and our human cells, they are 10 times or even 10 to 50 times more than this particular dimension. So this is the geometries where semiconductor industry operates. So now we have taken that wafer, and we will try. This is the wafer, cross section of the wafer. Wafer have to be, there is a like a very complicated process how to make these wafers from the sand. There should be pure silicon. There should not be any other material. But still, there are chances that there will be some carbon, some oxygen, and some other atoms may be there. But their density should be less than 10 raised to the power 9 per centimeter cube. As you are seeing these dots, these something white and black. So these are some other material impurities which are sitting on the wafer. So this is not acceptable actually. So this dimension is thickness is around 825 micron, and I need only top not more than 2 to 3 microns. Only because I will be depositing layer, I will be doing all my operations on the top layer. So my useful area is from the top only 2 to 3 micron. This much area is not useful. But then why I am doing? Then why I am taking such a thick wafer? Because this I have to handle it. It's a 12-inch disc. If it is 3 or 4 micron thin, you cannot handle. It will be handled by putting a pressure. So you cannot handle it. It's a very brittle. It will break. Another reason, it has to see temperature as high as 1200 degrees centigrade. So if it is this much thin, it will bow and it will break. So you need some mechanical strength and lot of stresses to take care of those stresses. So we need this, and once all operations are done, so this area will be cut. The remaining thing will be cut, and we will get only the top uh, thing where the die is. So the first operation is here also there will be some impurities. What we will do, we will do annealing, and there is a step which is known as gathering. This is known as a gathering, top side and bottom side. By gathering, what I mean is I will, whatever impurities are there in the top 2 to 3 micron, in the top 5 micron area, I will pull these impurities down. So you are seeing in the top surface, there is, it's a very clean. There is, you won't find any dot. So earlier it was like this image, and from gathering you can see this is area. There is no such impurity atom. So that is the meaning of a gathering, and this is done under an argon environment. So the top surface is very clean. And first area we will identify the areas where the component are made. That area is known as active area, and other areas by default are known as field area or isolation, where there will be isolation. And for isolation I will dig a trench, shallow trench. That's why it's known as a shallow trench isolation. Like in a wall, you have to dig a trench to, and then you fill it with something and do a small wall. So it's like that. And the resistivity, it's a silicon wafer. Resistivity is 1 ohm centimeter. As I told, it can be 1 ohm to 100 ohm centimeter, depending on the process engineer, what kind of process they have designed. So we will deposit oxide, pad oxide. Here, yellow thing, we have deposited pad oxide. And depositing pad oxide is simple. It goes in a furnace under oxygen, and the flow rate of oxygen is controlled. There can be dry and wet oxidation. They are different. The kind of oxide SiO2, it's not SiO2, it's basically SiXOY. How many silicon atoms and how many oxygen atoms make a bond? So depending on the quality of SiO2, these temperature, pressure, and all those things vary, which we study detail in the topic oxidation. But for the time being, we are depositing a oxide, which is also known as a pad oxide or a base oxide, and it's normally very thin, like 50 nanometer, 500 angstrom, even less than 500 angstrom kind of oxide is there. And then on top of it, we will put a, so here also the same thing. The whole thing, the green is a oxide. The green is an oxide here. And then on top of it, we will put a nitride. And so this is the how to deposit oxidation and things like that. You see here, there is a difference between oxidation and growing. So here we are growing because this is a silicon surface. When it reacts with oxygen, some of the silicon atoms here, they are consumed. So you can see here this level. So this much. So 40% of the oxygens are of the silicon atom, they are converted into SiO2, and 60% is on top of it. So it's like this. And there's a Niels model which they studied, and how this process takes, kinetics, how much time. There are mathematical equations where we can tell to grow 5 nanometer, to grow 50 nanometer, how much time it will take, what will the quality of oxide, how much temperature, how much pressure, everything is well characterized. And furnaces, as I told, there are vertical furnaces, there are horizontal furnaces. Vertical are better, they give better uniformity. And so as there is something which is called a boat. On boat, each wafers are kept. And furnace, they can take 100 wafers, 200 wafers, even 500 wafers, depending on the type of the furnace. These are expensive furnace, very well controlled. You can control temperature in the range of 0.05 degrees centigrade. So they are very expensive, and there are only 2 or 3 companies which make these things. And all these wafers, they have to get the same kind of environment, in the sense the gas flow rate and our temperature, pressure, they have to be same. then only the processing of on all these 200 wafer has to be uniform. And we are talking of a dimension which is 50 nanometer. So this is the criticality in all these things. So from there we can, after this we will deposit, this is the yellow, we will deposit nitride, silicon nitride. Ammonia is used, it is Si3N4. I cannot deposit silicon nitride directly on silicon because it's not it's chemically compatible, but there will be lot of stresses developed between silicon. It's a pure 100 double diamond structure, and there is a, which we call it a atomic spacing, a lattice constant. And silicon nitride is not a, it's a not a crystalline structure, it will be polycrystalline. So due to mismatch in the lattice constant, there will be a lot of stresses and strains developed, which we don't want. So, and there are some other reasons also, and that is why we have a yellow layer which is an oxide, and then we have a silicon nitride on top of it. And once it is done, you can see earlier green layer was there of oxide, now the silicon nitride also has come, and this is deposited by CVD, chemical vapor deposition. And after this, the photolithography is the area, because on this I have to define the areas where isolation has to be made, and
Sir,
where the,
j- sir, just to interrupt, sorry to interrupt. We have another 7 minutes, so you
yeah,
may
I
give
will
some time
finish.
for question and answers also.
Okay, so I will just finish within 2 minutes, and then we can have more time for question and answer. So in this, the photolithography will define that area where we can have isolation and where we can have these components. So this is the reticle which was I was trying to show you. It has that information, and based on these, this is the area which it has defined. And then we will put a photoresist, and there will be a mask, then the light will shine, and then depending on the positive photoresist or negative photoresist, the photoresist will be weakened, this window will open, and once this window is open, I will do the etching to remove this layer, which is blue color. Then I will use another window to etch out this yellow color also. So both these will go, but where red is there, nothing will happen. So that area will be saved like this. So I have made a trench. This is in short, and I have made a trench, and this trench has to be made at a certain angle. It is not 90-degree, as you can see. It's close to 105, and there are reasons of physics why it's 105 and how to make these kind of structures. So finally, then we have to fill this, and filling also is done in 5 to 10 steps because of various reasons, which I will skip. So the point is, it's a very overall interesting things. We play with a lot of new materials, with gases, chemicals, and end result has to be electrical, because finally my goal is to make a device which works on basically electrons and holes. How many electrons are there, and the electrons, the movement of electron will cause a current, and then this is how the device works. So with this I will stop, and I will if there are any questions, I will prefer people can ask questions.
Sure. Thank you,
Any
sir.
queries?
Thank you, sir. Thank you for a very elaborate presentation on the manufacturing process. I will kickstart with a couple of questions, then others can also unmute and ask. Based on what you presented, you said there are only a couple of companies which are manufacturing those tools, right?
Yeah.
And so the two questions that I have is, one is, what is the knowledge gap or technical difficulty in, say, a reverse engineering or coming up with a machine like that? That is one. Second is, even assuming I'm importing that machine, what is the real skill gap that people have? Because much of the education process may not give students to any exposure to this process itself, right? Other than a presentation kind of thing. They may not get any physical exposure to this process. So what is the real skill gap in getting people to actually use those machines to manufacture this?
Yeah, I will answer both your questions. The number one, like why there are only two or three companies. The reason is making these machines, it's not that easy. You require a lot of, you can say, expertise in various areas, not only the one mechanical aspect only, because these are very, very complex electromechanical systems. A lot of optics will be there, then a lot of robotics and other things will be there, a lot of programming will be there. We are dealing with very, very small, accurate dimensions, which are in like 100 nanometer, 200 nanometer kind of structures. Repeatability is very important. So the machine is handling those kind of things. And those people, they have spent, I think, billions of dollars in making those in the last 30, 40 years. We have not done that. And experience counts a lot. In a like very yes, answer is like Intel. Why only the processor in laptop servers are Intel? Why not other company? Or even AMD struggled, but they were not able to penetrate this. And the reason is they started in 70, 74. They started with a 4-bit processor, 8-bit, and they last 40, 30, 40 years. They have so much of database, so much of knowledge. So they are able to do that. So they have a lot of expertise in this area, and a skill set required in various disciplines is huge. It's not that easy to develop in that kind of machines. And the reason is now the second question is if we don't have a fab, then the process. You see, we don't need the equipment for first of all for learning the basic concepts. What is happening is even this particular the VLSI technology start very nicely at old IITs, at 5 6 old IITs, and those it's basically MTech level course, and those people, those students who have done MTech, they are able to get jobs very. I think I keep in touch with them. They are able to get directly in TSMC or other good global foundries. They have opened a big office in Bangalore, and they are paying 40 to 50 lakhs after MTech. VLSI students directly, even IIT Roorkee students, they got huge packages, because once they know the basic concept, once they work on the machine in their fab, they will pick up. They only some basic fundamentals and all those things are required. Certain fabs have been made only tabletop equipment, which are not industry standard equipment. Like IIT Bombay, they have a fab. They have spent 100 crore in in making that fab. IISc Sense fab is there. They also spent 200, 250. Transistor cannot be made, but certain deposition, etching, those things can be learned. Those concepts can be learned. But of course, not to that minute level, not to that sophisticated, small dimensions. But the basic processes can be learned actually. But practically also doing the theory and then doing practically on those. And final thing will definitely be on the machine itself. One has to invest a lot in this, and you need a lot of money in this, and many countries have not been able to do that. Only fabs, even in Europe also. There is no fab in UK. Only one in German. No fab in France, Switzerland, some other countries also. So a lot of money is required in the initial stages, and the government has to subsidize this. And you see, even now, the Indian government is capex is being subsidized by 70%. So that is the reason some Tata has come, and one or two more companies have shown interest. In US also, they are paying huge amount of subsidies to set up these and for R&D purposes. So huge amount of R&D is budget is there. In India, we don't have that kind of, though we have very capable engineers, but R&D budget is limited in the government, and private doesn't give any money. So that is the reason why these particular things have not happened. Even you can say the jet engine. Now there is a crash. There was a crash in the plane. People were saying we should have our own engines, and we are getting 404 engine from General Electric. But people are talking of jet engine, but we don't have a good engine for a scooter or a car even now made in India. So how can we go to a level of a making a jet engine? So all these things have to be the country has to take care, invest a lot initially, and then only some result will come. Initial R&D requires huge, you can say, money in terms of making these labs, making good people work for an R&D. Good people don't work as an R&D engineer. They prefer marketing job because the salaries are more there. and mental work is also less as compared to R&D. So there are a lot of things, and R&D ecosystem is not there in India.
Okay. So over to any other questions from the members here. Please feel free to unmute and then ask.
Sir, thanks for the great presentation. My name is Shri. I'm a faculty from NIT Trichy, specializing in instrumentation. So you mentioned that there is a lot of investment that is required in order to firstly understand how these machines work and also to either build or operate these machines. Yes, sir.
True, true.
So, so even if we make all this investment, like what could be the byproducts, I can say, I mean, apart from making that transistor, so is there
Sure.
any other hidden benefits for the industry as such?
You see, my view is we have to focus on the design where the investment is also not much. We only EDA tools, which government is already providing, and we have to focus on the product as per our Indian requirement and try more on the product, right? We don't have in Bangalore, all companies, there are design engineers are there, as you are aware, around one third 20% of the total world's design engineers are based in Bangalore and Hyderabad, but we don't have any IP of ours. So these Qualcomm, Apple, Broadcom, these people, they were started by two, three companies only. They worked in Intel. They acquired the necessary whatever know-how, and they started their own unit. And now these unit, now each is having, you can see their turnover is more than 10, $20 billion kind of business they are doing. So whereas in India, the design companies, there are startup, there are design companies, but they are not big. They are having only under 200, 300 engineers, not like Intel having thousands of engineers. So we have to focus on product basically. Product design, I mean. Product manufacturing is a different ball game. Product manufacturing requires a lot of money, lot of expertise. Why to handle that? There are many like Apple, they are not doing. And there are other companies, Qualcomm, Broadcom, Nvidia, for example. Nvidia today is a 5 trillion valuation. It's more than our economy. They don't have fab, they don't have manufacturing. They have only the design. And you see their 5 trillion, and TSMC valuation is, I think, 1.5 or 1.6 trillion. They have the fab. And manufacturing is not that easy. There are a lot of things, and making profit in a manufacturing is any manufacturing job. Your margins are not much. But once you have an Apple, you can see Windows, Microsoft, you can see how much money they have made. Apple, you can see. Apple doesn't have any manufacturing. They are not doing any manufacturing. They have established their contacts. They are doing design, product design. Unfortunately, we don't have a product, Indian product, even in the software, which we call it our a lot of expertise, lot of people in the software, but we don't have any product in the software. Like China, they have their own WhatsApp, own Facebook and Twitter, things like that. We don't have any good software, even a good email also we don't have. So we have to think in terms of what we can do in this area, particularly the product design that and pertaining to our Indian requirement. And one good example in this is like we have our own NAVIC system. ISRO developed the GPS because GPS is a American system, and in case of military applications, they may restrict you, they may not give you the information. So each country should have their own GPS. So we developed our own GPS. It's not worldwide. It's only catering to India, Pakistan, Sri Lanka, and neighboring countries only, South Asia and neighboring countries only, because we have only 7 satellites, whereas USA has 35 or 40 satellites. So, but NAVIC, then you need a receiver at the ground, and you need the electronics which is sitting in the satellite. So that has been developed in India, the entire thing. And but that chip is not doesn't go in the mobile phone, because mobile phone IP is not ours. It's a Samsung phone. Why he should put Indian GPS chip there? And they are putting American chip only. American, which caters to American GPS only. So we don't have a design of mobile phone. Whereas China is not the case. China, they have their own mobile phones. They have their own, you can say, telephony capital equipment, like tower. There are equipment which goes in the mobile phone towers. China has made that. They have their everything on. They have their energy meter, their own energy meter. We don't have. 3-phase, 1-phase, lot of houses, the pacemaker and things like that. There are so numerous examples. Smart card is one example. We couldn't make even our own smart card. And it's not a very high tech, it's a very small processor and some memory. And everywhere your driving license, RC, medical. So it's a huge business making smart cards. So all MNCs are doing. So it has to be done in a product rather than what I feel, have some product and get it manufactured and slowly build manufacturing also.
Thank you. Thank you,
Um,
sir. We can
yeah,
take one
good
last
evening.
question.
Yeah.
Yeah.
Good evening, sir. My
Yes.
question is, first of all, you rightly said we still have this layered chip making nowadays. So design, we have a lot of scopes. This GDS file you talked about, this can anybody read this GDS file to get the detailed picture of the design of the transistors?
GDS, yes, madam. GDS file can be read in that particular software on a
Okay.
on a workstation. You can know that. You can at least get an idea of what kind of design.
Yeah,
You
that,
can do the
because last,
back engineering. You can
yes.
do back engineering.
Is this easily available? Like there is nothing
No,
like
no, 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 no. They
No,
won't.
it
They
is
won't
not.
give. No, nobody will give.
Okay, that's the problem. So how to get those information about the location of these transistors and all? If somebody
No,
wants
no,
to
they
work
will
on
not. That there are some companies in Belarus, they have developed that each layer by layer, chemically they are able to remove
Okay.
the layers and do some
I
drawings. That expertise, there are 2-3 companies in Belarus who can do
Okay.
this.
Mhm.
Normally GDS layer they won't give. That is an
Okay.
IP, they normally they won't share those.
Okay. So that's the trouble. Okay. Thank you.
Thank you, madam.
So thank you, sir.
Sudhir,
Yeah,
I
sir.
just want to
Yes.
make a remark.
Yeah.
Thank you very much for the 2 lectures in providing an overview of this industry, not just locally, but also globally. One of the things I want to mention is for those who have not seen it, if you go to the Cree website, Professor Jorg Schulze has given 2 talks on how they are experimenting with teaching manufacturing of semiconductors in Germany. You will find it very interesting as to how they are blending the theoretical and the skill base of actually running a fab within a university. It's a quite interesting set of lectures. I thought I might tell you about it so that other people can also go see how they are approaching this whole problem of semiconductor design and manufacturing.
So some link is there, sir, if you can.
Yeah, the Cree website link is shared. I put it in the comments.
Okay, sir. That's good.
Yeah, I think it is one of the early talks, first 10 or 15 talk or something like that. So thank you, sir. Thank you, Sub. So thank you all for joining today's 58th talk. This will be the last talk for this year. The next talk we will start on 7th January. So with that, thank you again and wish you all a happy new year. Very early message from Merry Christmas and a happy new year as well. Thank you.
Thank you. Thank you, sir. Thank you.
Thank you, sir.
Thank you.
Same to you.